All right. First, let's quickly recapitulate what we have seen so far. In last class, we have seen uh, what have we seen? Last class. Yeah, last class. Acha, I don't remember. This is what we have seen. We have seen how to define a user defined primitive. Like the primitives are nothing but the user defined functions, isn't it, in Verilog? And we have also seen an example of what was that? Event detector, odd detector, and the decoder. We have seen the decoder example, 2:4 decoder, isn't it? And meanwhile, we have also, at the end of the class, we have introduced the concept of vectorization. How can we define any input or the output variable as a vector? That is what we have seen. And finally, we have seen what is called as a data flow modeling. Okay. So far we have seen two types of modeling. Which are those? Can you tell me? Yeah. Yeah, so gate level, which is called as also structural, and data flow. Okay, so how to recognize this? See, this Verilog allows you to write the coding in various forms. So the first one, what I said was the gate level, or what is called as structural programming or structural modeling. How to recognize this? There will be we shall be using, will be using the already defined primitives. I mean already defined keywords like for AND gate, OR gate, and so on. We will be using this. And what do we call using when we use these keywords? What do we call it? Yes, it is called as an instance. XOR, NOT, and so on. NAND, NOT, and so on. The second one which we have seen was a data flow modeling. How to identify this modeling, or how can we code in this? I mean, if it's AND, we need to write some statement like assign. So there is continuous statements, continuous or a series of assignment statements, and then you can specify that A and B and so on. So there is continuous uses of this assign statement. So if you see assign, it's a data flow. If you see the gates, it's a gate level or structural. There is one more modeling which is called as we have also discussed the difference between this and AND. Okay, we have seen that. Then the third is called as a behavioral modeling. Now in the behavioral modeling, okay, we make use of we avoid this. Okay, assign statement, we don't use gate, we simply specify the behavior of the circuit. Like it may sometimes be useful, like there may be some circuit whose inputs and outputs we know, and we also know its behavior, but we may not know how the structure look like. So if you are not aware of the internal structure, go for the behavioral design. So in the behavioral design, there is a what is called as a statements, or a kind of procedural statements, what we say. Now this is not different from the others, like what are called as a procedural statements. So these procedural statements are nothing but the statements in which the logics are assigned in different fashions. Like we have seen one of them previously. Like we have seen this initial. So initial is nothing but initial begin. Do you remember this? Initial begin. Where do we write this? In the test bench, isn't it? And we write some statements, and after that we end this. So this is again a procedural statement. Why procedural? Just because whatever is written inside this will get executed as per the the order of the statements. But this we now any module. What is module? As I said, it's a basic structure of any Verilog function. So they may it may have arbitrary number of such what is called as a procedural statements. Okay, so this is one among them. So we have seen initial and end. There is one more which is called as a always. So initial is something, initial procedural statement, it executes only once. Okay, in the test bench we have seen that after initial begin we specify after how much delay we should how the stimulus should be varied. So it gets executed only once. But what if we always want to check it? Okay, like for indefinitely we want to make something happen. So that can be done using always statement. So the syntax is always @ and the condition here. So usually this behavioral modeling is useful while modeling the sequential circuits or flip-flops. Say for example, we need to monitor when the clock rises or when the clock falls. Like we need to monitor, we need to act when the positive edge of the clock comes or a negative edge of the clock comes. So that is where this, now that we can't specify in the initial or end. I mean that is not executed one, it is executed every other time when the clock is executed, isn't it? So we want it to happen always. So always @ and the condition. So it may happen that okay, we want the condition to be like clock. We may specify that clock. What does it mean? I mean when the clock is 1, then you should go for the next. I mean then the statements below this will be executed and so on. We may also specify the specific transition of the clock. Say for example, I may also specify always @ pos age. Now this is again a keyword, positive age of the clock. So this will execute only if the positive age of the clock appears and so on. We may also specify the negative age. Okay, so negative age is neg age and again clock and so on. Or I may simply specify clock. Now here there is no, I mean this, can you tell me where it will be useful? Only not ages, I am specifying directly the clock. Yes, in the latches where the level sensitivity is expected. Again I may specify other statements also. Say for example, see all the models which we have seen so far, all the programming which we have seen so far, like half adder, full adder, whatever we have seen so far, we can model all those designs using behavioral modeling also. Say for example, I need to implement a 3 input OR gate or 3 input NAND gate or 3 input AND gate, whatever it is. So I may specify that always add the condition to check is like say A or B or C. I can specify that. What does it mean? You need to execute the statement. Now after that I can specify, like say for example, I need to implement a 3 input OR gate. So I will say that always add A or B or C and begin. I may say that okay, the output, let's say it is a D. So D equals to A or B or C and so on. So I mean this also very well executes and gives you the result for 3 input OR gate. So this is what is called as a behavioral modeling. So whenever you find this always or this initial, I mean some kind of procedural statements or the behavior of the circuit is specified, you name it as a behavioral modeling. Now we may program it in mixed way also. I mean you may sometimes specify assigned statement, you may sometimes specify AND gates, OR gate, or I mean the mixed modeling is also possible. So the fourth is like a mixed modeling. So you can very well go for the mixed modeling. or hybrid modeling. And the fifth one, which we shall not consider in this course, is what is called as a switch level design or switch level modeling or switch modeling. Now if you remember the very first day of a course, okay, in that I have shown you a video or a structure of an IC. How does IC look like? Okay, so what is there inside that and so on. So in that what we have seen was like, now are you getting the levels of abstraction? Like for different levels of abstraction we have different designs. Say for example, the IC, you have the IC, or some model, you have some structure, and you simply know its behavior. What is its behavior? Go for behavioral level of modeling. Suppose you know its structure, what is there inside it. You may say that okay, there are two AND gates and followed by an OR gate. Okay, if you know the structure, and if you simply need to if you simply are bothered about joining them, go for what is called as a gate level design and so on. So I may have something like this structure. So I have a modeling for what is called as a behavioral. I have a modeling for what is called as gate level. Now data flow is modeling is nothing but we make use of the Boolean expressions. Okay, I mean like I may not specify that this is the inbuilt primitives or inbuilt keywords we will not use. Data flow is somewhat similar to the gate level, but not exactly. Okay, we may not use this, but we may say that okay, there is simply a wire which is available W1. So I may specify W1 as assign this W1. Sorry, the spelling is wrong. Assign this W1 as the AND A and B and so on. So if this is A and this is B, so this what is called as a data flow modeling. And at the level of abstraction, if we go again the deep of this gate, okay, we may have inside this gate, inside this gate there will be some transistors or the switches. So we can also design with respect to the switches, which we are not going to consider. So what is called as a switch level inside this. So let's switch level design, switch level modeling, which we will not consider. Alright, so as I said, now we are going to see today some examples of behavioral modeling. So as I said, this behavioral modeling is used to model sequential circuits. So let's take some simple sequential circuit. Let's say it's a D flip-flop, and let's expect some output. Say for example, we expect to give suppose now for any D flip-flop, now let's consider the black box. Okay, let's consider it as a black box or a white box, whatever you want to say. So D, how many inputs you tell me? There is only one input, which is D. What else? There is a clock. Clock may be positive edge, may be negative edge, but again it's an input. So it's a clock. The output we have Q and Q bar, and we know its behavior. I mean, it will simply, how it behaves, it will simply copy Q. The data will be simply copied from D to Q. That's why it's also called as a transparent flip-flop. And when will it happen? Only during the positive edge of this clock. Okay, so we may specify a clock. So for this purpose, we'll require a clock which will always be like a free running clock. I mean, which will always oscillate between 1 and 0. So we'll require some waveform, something like this, isn't it? and so on. And we just bother about when this positive edge comes. Data may be anything. Okay, data is incoming, so it may vary, not according to clock. Just see what I said was system clock is independent. Okay, it doesn't depend on anything else, but the data has to be dependent on the clock, just because the elements are like that. So what I may do is I may select some data in some specific fashion. I may say that during just before this I may make this as a, or I may start with 1. Yeah. So I'm having something in my mind, so I'm specifying this data something like this. You got it? I mean, during positive edge I'm making sometimes it's 1 or sometimes it's 0. During positive edge I'm making 0 and 1 and so on. So this data may vary anything, right? So I'm taking all the possible combinations of 1s and 0s. So let's say this is D, this is a clock, and we know what we want as output, right? So this is a positive edge. Just specify these lines. Alright. Now what is the behavior? It will simply copy the data when the positive edge arrives, right? So let's quickly go to directly to the coding page. Okay. So we know what is the output. You tell what do you expect the output as? You tell me. I mean, during this positive edge, okay, I forgot to mention this. What is the output here? You tell me. As soon as during this positive edge, what is the D? It's 1. So output we expect it to be 1. Assuming that the initial it's 0. Okay. So assuming that the initial value is 0, as soon as this clock appears, it will immediately go to 1. It will retain the same value as long as the next change happens. Here it will go to 0. Here it will retain 0. Here also it will be 0. Yeah. Then here it's 1. And it will retain that. This is what we expect as output, isn't it? So out or Q, and Q bar will be simply the opposite of this. Okay. So this is what we expect, and this is what we need to model using what is called as a behavioral model. Yeah, otherwise it will be difficult. So let's go to the coding page. Open edaplayground.com or visit our website. If you don't have internet, you can connect it to mine. Alright, so we'll go with the usual procedure. Yeah, step 1, define module. Module, it's a D flip-flop, so write DFF. So it's a module name, you can specify any name there. Followed by, tell me, what should I write inside this? Yeah. What is this called? A module. This is a keyword. What is this? The module name. What is this? In parentheses, what do we need to write? Ports. Always remember the inputs and the output ports. What are the ports? First you will require a clock, which is an input. After that D. Outputs are Q and Q bar. So I am specifying it as Q and QB. Is that okay? Don't forget to give semicolon. Then you need to specify the directions of the ports, because it may not know which are the input ports and which are the output ports. Specify input, which are the input, clock, then D semicolon, output Q and QB. Alright. After that, the procedure is now we need to go for the behavioral design. In the behavioral design, we should write with, now here we can't use and or not. Okay, I mean we don't know what is there inside that. If you know the behavior, see we can very well specify it using gate level design, but we'll have to specify, okay, iska output iska input ko jayega and so on. I mean it will be tedious job. In behavioral design, we just need to specify its behavior, how it should behave. So in that we should say what? Assign, no, so not assign, so what is that? The keyword, I've just told you the keyword. What is that? Always. Always. Now see, always when do we want the output to be present? Whenever the positive edge of the clock appears. So you should specify pos edge. Now pos edge is again a keyword. So always is a keyword, pos edge is again a keyword. Pos is of what? The clock. So specify clock. Alright. Inside that, you can say is begin. What should we do? What do we need to do? We need to simply assign the Q to D, right? D to Q. So Q equals to D. That's it. And QB as Q ka complement, isn't it? So complement I should write it as like this, isn't it? Yes, please. This is okay. Now should say end module. That's it. Now see, whenever I say, now this is what you tell me, and this is what is called as a procedural statement. In the procedural statement, okay, now there are again two types of assignments. We'll discuss them. Okay. So, all right. After this, now that's it. We don't need to, I mean, worry about what is there inside. In the test bench, on the right, on the left, sorry. You come here, no problem. Come here. Yeah, how to specify test bench? Module, a different name. So I'll say that D flip flop car test bench. There's no variables there. Reg. So I'll simply copy them. Now this code will throw some error. Okay, let the error come and then we'll address them. After that, yeah, tell me, what do we do after this? So input we are meaning after the reg. After this, again the procedural statement. As I said in the test bench. Now what do we want in the test bench? You tell me. In the test bench is nothing but we'll specify the stimulus to be given to the circuit which we are going to design. So the stimulus is like, there are two types of waveforms which we expect to give as an input. Which are those? We want the clock to be free running. Then we want the D to be varied somehow. Let's take clock first. Let's define the clock first. I am specifying at initial, begin, and let's specify the clock. Now we want the clock to be varying from 1 to 0, 0 to 1 and so on. So let's say clock to be initially at 0 and we want it to be repeated several times. So there is again a keyword repeat. So see, it's not necessary. What we can do is we can simply specify a delay of 10, let's say 10 units, and we can simply vary this clock to 1, but we'll have to write it several times. So instead of that, what we can do, we can simply write a keyword repeat. How many times you need to repeat? Let's say 10 times. although we don't need, but no, let's specify it as a 10 times. What do we need to repeat? We need to, after when the clock is 0, we need to specify some delay for which the clock will be 0, and then it should make 1. Specify some delay there for which the clock will be 1, and then it should jump back to the 0, and so on. It should continue. So I'll specify the delay. Let's say 2 units, and after that I want this clock to be complemented. Okay, I mean in general I will write that complement the clock. So I think this should work. And so what does it say? Initial, make the clock 0, repeat 10 times. What do we need to repeat? The following statement. What is the following statement? Give us the delay of 2 units. After delay of 2 units, complement the clock, and you need to repeat this 10 times. This is what it means. Now this is all about the clock. We didn't specify what are we left with. Yeah. So what we'll do is initial, again, see, as I said, I may give an arbitrary number of this such procedural statements. So I can again specify initial, begin. Now you may ask the question that why can't I specify the same D inside this? Okay, that I'm going to answer that. Okay, first let me complete this. So what do I want? The D, I want it to change to, now initially I am expecting that to be 1. How do I need to change that? Now this is what the waveform I am expecting. 1. Now see, how much is this? Now let me specify this. So this is okay. What have we specified this delay? 2, right? So this is 2. What is this one? This is also 2, right? I mean, I didn't draw accordingly, but this is also 2, and so on. When do we want this clock to go down? Initially it is 1. So after how many times it needs to be to go down? So it's 2, 2, and after 5 units we need to make it 0. Okay, so I'll specify that. So after 5 time units I want to make D as 0. Is that okay? Then go back to this waveform. Now after this, now we are here. This is after 5 nanoseconds or 5 units. After that we want this to be 1. After how much time? I mean this is 2 and 1 you can specify. Okay, 2.5 you can say. 2.5, and we need to make 1, and suddenly we need to make it down. So I'll specify that as after 2.5 you make this as what, 1, and suddenly you make it 0. Now sudden things it may not happen, but I may specify a delay of, let's say, 0.5, and let's make it to 0. Okay, so this is alright. And then what do I want? Yeah, after, let's say, again 5 nanoseconds I want, or 1 nanosecond I want it to be making at 1. Okay, so 1, after 1 time unit I need to make it as 1, and after that it will be there for, let's say, 4. Is it for 4? Yeah, for 4 maybe. So you can change the timings. Okay, if you know what I am up to, okay, you can specify your own timings. So let's say after, let's say, 2 I want to make it 0, and so on. End module. That's it. What are we left with? We are left with many things. First we need to specify the instance. So the instance can be specified by simply copying this. The only thing is, the instance specifies the linkage and the instance name inst. After that I need to specify the dump file without which the simulations won't run. So dump file, give the file name, let's say it is dff dot vcd. Was it vcd? Variable change dump vars. So I'm specifying one there. I'm not going into much intricacies of this dump file. I mean, very in depth I'm not going. Okay, I mean, I may specify. See, one I already told you. One is like it will simply dump the variables in the current hierarchy. Okay, 0 is again it will dump the variables in that hierarchy. I mean, it will not dump the variables in the lower level of hierarchy and so on. So it depends on what level of hierarchy you need to save the variables. That's it. Is that okay? Now we expect this to run, but definitely it is going to throw some error. Let's see. I'm going to run this. Okay, you need to select a valid simulator. So alright, so I'll specify the simulator as open source Icarus 0.9.7. open epwave. After run, I'll enable that option. If I run this, I expect it to run, but it may show some error. So what has it shown? So in design 2, okay, there is some error. So in design, line number 2, what is that? DFF. Okay, the error is clock is not declared within the module. See, I have specified this clock as C is capital, so it's a what is called as a case sensitive. So I should specify it as small. Okay. After that, the error is in line number 8. Is this here? What is the error? Q is not a valid left value. Okay, L value in DFF underscore test bench. What does it indicate? See, the thing is, you might have noticed in the test bench, whatever we specify in the initial, okay, in the initial loop, whatever we specify, this this variables which we specify it as reg. Have you noticed? I mean, in the test bench, whatever we write in the initial begin, we specify them as reg. So it's always true with any procedural statements. No matter it's an always statement or an initial statement, okay, you need to specify the variables as reg. Okay, so okay, I will specify this as reg. But if I specify them as reg, again it may show some error. Let's see what. So if I make them as reg, it will show some error saying that okay, Q is declared as a wire and Q is not declared as a left value and so on. So not here. I should specify this output, na? Reg. Whatever the variables are there inside a always loop or a procedural statement, that I should specify it as a reg. Okay. If I run this, again it will throw some error. Are you missing input and output declaration? That is what it shows. That means you need to specify the directions of the input, and in addition to that, you need to specify it as reg also. So what I will do is, I will, without changing this, I will specify as reg. So I may update the declaration of the variables, okay, post declaring it as a input or output port. So I will specify reg as Q and Q bar or QB. You got the meaning of this? See, what I am saying is, this always or initial are the group of what is called as a procedural statements. Okay, procedural statements are something which are defined inside this initial or the always loop. What is the difference? The initial loop executes only once during the simulation, after which it will stop. Okay, we didn't specify when it should stop, so I will specify that after, let's say, 2 nanoseconds it should stop. So finish and so on. And what is always? Always again a procedural statement which will always check the value. Okay, it will execute and re-execute indefinitely. What is the condition to be checked? As long as this is a positive age of the clock appears, this is what the condition is. If the positive edge of the clock appears, if this statement is true, then it will execute, otherwise not. Whatever is there inside this, okay, whichever variables we are defining inside any procedural statement, that has to be declared as a register. Okay. In the main module, we need to make sure that in addition to declare it as a register, we should also specify its direction. Now this must. You can't avoid this. I mean, the port declaration as an input or output is must. In addition to that, we need to also specify it as a register. Okay, clear? Fine. I think now we expect it to work. Let's see if it works. Okay, so is that? Not see the errors. How to bring back this? I'm not able to see this. Okay, I'll simply run this. Let me see what error it pops. It's showing some error, but I'm not able to. Yeah. Okay. So what does it say? Error is at 2 says that clock. What? It's not declared. And okay, so what is that? Let's see. DFF clock DQ. I think this clock should also be. Let me see. Can you see the error? Can you check what it is? Clock 1 of the module, DFF is not declared. Declared this. Something is missing. Five dredge. I'll run this again. Sometimes debugging may be tedious job, so two errors, no via. Alright, so QB is a port declaration. Test bench 3.5. well, getting that. Alright, let me see some example. Alright, so I think I didn't specify. No need to clear this. This should not matter. Let's see. Can you find the error? What is this? Port clock 1 of the module is not declared. Are you getting this error? Same? Huh? Achha, only I am getting, yeah. There should be something wrong. What is the error that you are getting? You are running clearly? Sure. Error at 7. We need to specify this. Okay, I think the C is capital. Okay. So sometimes small c and capital C. So I have, alright, so yeah, fine. So my mistake was, it's sometimes tedious to find or debug the thing. Okay, the mistake was I specified this capital. उससे जो कैपिटल का झंझट ही मत रखो, सब स्मॉल ही रखो, ठीक है, स्मॉल ब्लॉक एंड सो ऑन. Alright. Now I'm getting some different error. Design 7, so I should not specify this. This is not required anyway. So this is not required. So see, you should remember that, you know, this after always you don't need to specify the semicolon, otherwise it will pop an error which is otherwise necessary. Okay, see, इसको पकड़ो, फिलिप्स मूरबाय जिसने बनाया था, उसको पूछो क्यों नहीं दिया उसने. So this is like a syntax is like that, so we don't need to specify that. Yeah, so let's see if it runs accordingly. If I run this, I'll get some output. Is this the expected one? Q. Alright, so when do we expect the output to come? During the positive age, right? during the positive edge of the clock we should expect the output. So let's see if it appears. So where is the positive edge of the clock? So initially, yeah, this is the positive edge. What is D? So see, what is red line indicates? It's, I mean, unknown. This ray indicates X. If you click on that, you will get X, because initially we don't know what is that. So it has quickly gone to 1 as soon as the clock appears. It will retain that value till the next clock comes. When as soon as the positive edge appears, what is the D value at that time? 0. So it will go back to 0. Again it will wait till the next positive clock comes. Okay, then it will make to 1 and so on. Are you getting? I mean, initially it is unknown, went back to 0. Sorry, it went to 1 as soon as the positive edge appears. When the next positive edge appears of the clock, okay, it went back to 0 just because at that time the D was 0. After that, as soon as the next positive edge comes, what is the D at that time? Now see, I should have specified less time delay here. Okay, so let it be, now let me reduce that. So when it is 1 and 0, no? D is going 1 and 0, let me reduce that. Let it be 5. I think 0.5 doesn't take, lowest is 1. So we can specify this precision also. Okay, I mean, see, by default the precision is 1. I mean, we can't specify in 0.5 of that, but we can always change that. We can always change that by giving the there's some syntax for that. I will tell you later. So instead of that, what I will do is, instead of this, let the clock vary for, let me run this. Alright, so during positive edge it is 0. I don't want this. So how can I specify that? Increase the clock. I will increase to 3. And I will repeat that for, let's say, 20 times. Alright, now it should work. 1 and 0. 1 and 0. Are you getting what I am doing? See, I am just changing the inputs so that you know that the transition should not match. See here, I mean, the D I am changing that it should happen in between that, because you know, if it is if it is there on the transition, we don't know what the value would be. Okay, so I have changed the input in my fashion. You can give your own input. How can I avoid this unknown state? I can specify what is the initial value of that Q and Q bar. How can I do that? See here in the range itself, I can specify that Q as initially to be 0. I can now QB you should not define, because QB is like okay, initially you can define this QB as, okay, let's not bother about QB, because for that you will have to use the assign statement and all. Okay, let's run this. Oh, I'm getting an error. QB is declared as a हाँ किसके लिए? हाँ वेज, ओके QB admin space, right, good. So initial value of q is gone. Okay. Similarly, we can make this happen, qb. For that purpose, we'll have to initially write that qb. Now, wait, I have simply just avoid this. Okay, qb as bar of q. I'll explain the code again. Okay, invalid. Okay, I should write assign here. Alright, that I should not do. Okay, I can specify it directly. qb as 1. That's it. Now there should not be any, and you should see the q as complement of qb. Everyone is getting this output. सबको आ गया ये output? Getting? नहीं है. So those who got this output, go for implementation of T flip flop. Okay, T flip flop. So don't forget to save. Okay, let me first quickly explain what we have done so far. Okay, those who missed, just kindly pay the attention. Okay. First thing, the aim was to design a D flip flop. So we went with the usual way using behavioral modeling, just because the structure will be very expensive one, gate level will be quite expensive. Expensive in the sense of coding, I am saying. Very well you can go for gate level or structural or data flow, but we'll go for a behavioral. In behavioral modeling, we are just aware of the behavior of the circuit, we don't know what is there inside it. Here we didn't specify what is there inside it, but we know how it behaves. So such kind of modeling is called as a behavioral modeling. It always has such kind of what is called as a procedural statements. So we have already been known about the procedural statement. One of the procedural statement which we have been using is called initial, begin and end. And this is another type of procedural statement which is always begin and end. What are the difference? The difference is the initial statement is executed only once, always is executed several times. It will re-execute, okay, as long as the simulation doesn't stop. In that we specify the behavior. What is the expected output Q? It should simply transfer to D. Now see, there is a difference. See the equality operator. Now you can pay attention here. So this equality operator, meanwhile I simply wrote this statement, okay, I mean less than or equal to. I can specify that also, and still you will get the right output. If I run this, you will still get the right output. There is a difference between that, okay. See, you will still get the output. Okay, this initially you may not get, okay. So I'll simply avoid this. So there is a difference. What I am saying is there is a difference between this and less than equal to. I will tell this different. The difference is whenever the less than or equal to appears, the statements are executed simultaneously at a time. Okay. So what is called as a, now let me specify that. What is called as assignments. The assignments are of two types. So this is called as a non-blocking assignment. Blocking assignment. This is called as a blocking assignment. And this is called as a non-blocking assignment. In non-blocking assignment, okay, all the statement. See what happens here is, let me explain that with the example. What happens is, whatever the value of D, if I specify less than or equal to here, whatever the change happens to D or Q bar, okay, it will be stored in some temporary variable and it will be transferred to Q and Q bar respectively at a time. But that is not true with this. In this it will happen with the procedure, like it will execute D equal to Q equal to D first, and it will execute QB equal to Q bar next, and so on. You may see the difference in the output. See, if I specify like this, you will get the correct output. D will be transferred first to Q, and then Q bar will be transferred to D. Q bar, Q bar will be Q bar will be transferred. See here, but that may not be true when you specify less than or equal to. See here, at the time it will run. So what is the initial value of Q? It is 0, so it will specify it as 1. See here, you can see the difference. Initially the Q was 0, right? The complement of that will be reflected at a time. Okay, so that's the difference. So better way to, I'm going for this. So the thumb rule is, if there is a procedural statements involved, go for equal to operator. If there is like, we may want everything to be executed at a time. At that time you can go for less than equal. Okay. Again, the thing to note is, all these initial statements, all this, whatever the keywords, this initial procedural statement, this is again an initial procedural statement. All these initial statements or the procedural statements executes parallel. So let me write that. So what I'm saying is, the point to note is, we may specify any number of procedural statements all are executed simultaneously. Now the thing is, now you may appreciate why I have written two different initial statements. Why didn't I write it in single module or in a single initial declaration? See here, what I am saying is, I could have simply copied this. I could have written all these statements inside this itself. Can you try it? See what happens. See, what I am doing is, I am simply copying this. Okay. So initial begin, I will simply dump this here, and then D I will declare it here. And why do we need 2 times? Let's see what change happens. And this I can simply write it after this. Sir, are you getting the change? What I am doing? I am simply avoiding 2 initial statements. I have written everything in one. Let's see what happens here. If I do it, okay, I'll still get the output, but that may not be correct. See here, what happened? After the clock कितने बार repeat किया था मैंने? 20 बार, 10 बार जो भी है. तो कितने बार किया था मैंने repeat? 20 times. Okay. So 20 times it will go 1 0 1 0. So 1 0. This is 1 2 3 4 5 6 7 8 9 10. 10 times 1 and 10 times 0. Okay. After that the data has changed. So what I am saying is, the initial statements execute all the initial procedural statements execute at once, but inside those statements, the statements are executed one after the other sequentially. But we don't want that to happen. We want the clock to vary and data to vary at the same time. That's why we have given them in a separate module, so that both the initial statements are getting executed at a time, and also the waveforms appears simultaneously. Is that okay? So I'll just redo the change. I'll just undo and I'll run it again, and I'll get the expected output. All right. So is this understood by everyone? Because this somewhat, somewhat tedious, but yes, I mean this is very important. Just because all the while we'll be doing behavior root model. Now we are done with the D. I am asking you to go for T, and once that is done, you can design anything. So I'm expecting you to write your own your project. Okay, whatever your project was, try to model it in Verilog. Try to do that at least. That will be a very good practice for Verilog. Okay, so yeah, everyone is getting the output. Anyone who is not getting, you're not getting. So go for T flip-flop. Okay, that will be very good practice for you. Whose lecture is there now? Huh? अभी lecture किसका? नहीं होगा तो फिर अपन कंटिन्यू करें. Yeah, whose lecture is there? Maths class. So who is going to take that? Ma'am? Anu ma'am. Can you check if she is available or not? Tell me just who are present. Roll number, okay, roll number. Jade is not there. Vazurkar not. Mayur is there. Mayur is not there. Divesh no. Atharv, Ruchita, Nilay, Aisha. Kunal is there. Dinesh is not. Sanket is there. Vinisha, no. Sanket Kari. No. Veda is here. Raj is not here. Sakshi, Prachita, Vaibhav, Aman Kumar, Diveshri, Shravanti is not here, Saurav, Tejas, Arun Kumar Banawat. Who else is remaining? Okay, sir? Very good. Alright. So go for T flip flop. T flip flop आ गया सबका output. In T, first see, you should always begin softly. In the sense, you should see how the model looks like first. Because we are just bothered about how it looks like and how is it behave. How does it behave? So we have only one input, isn't it? I mean, apart from the clock. So, including clock, there is a clock, and assume that it's a negative edge, so that we will get the flavors of both of the designs. So, assume that it's a negative edge, and let it be T. This is Q bar, and yeah, if we go with the same waveform which we have drawn earlier here, so this is the output for D. Can you tell me the output for T? See, what is it now? Instead of D, this will act as a T. Okay, I'll draw the next waveform. How is the behavior of T flip flop? Okay, as long as the T is 1, whenever the next clock edge, negative edge clock appears, this will simply toggle the value, isn't it? That means what? We'll have to assume some value. So go for the coding. I'll simply draw the diagram. जिनको ये आ गया तो उनको बिहेवियरल मॉडलिंग थोड़ा बहुत समझ में आ गया. ओके, टी फ्लिप फ्लॉप जिनको आ गया. See, I mean, how to conduct the exam for this? I mean, whether should I keep it internet open or online open or how? I mean, क्योंकि कैसा है कि अगर मैं ओपन इंटरनेट रखता हूँ एग्जाम, ओपन बुक्स, ओपन इंटरनेट, ओपन डिस्कशन, एनीथिंग इफ आई राइट, और नॉट ओपन डिस्कशन, ओपन इंटरनेट इफ आई गो फॉर इट, देन पेपर विल बी हैव टू उस लेवल का होगा. ठीक है, मतलब इंटरनेट पे भी जो नहीं मिलेगा वो डालना पड़ेगा. If you don't go with the internet, then how can you simulate? Then I will have to specify the code and you will have to find something. So let me see. I mean, I will have to take permission from Dean for that. So be ready for both. Be ready for both. So we may go for offline examination, pen and paper, and we may also go for online examination. So I am just bothered about which edge, negative ना, पहले मार्क कर लो negative edge. For the negative edge, okay, as soon as the next, see, if the negative edge is appearing, T is 1, what do we expect the output to be? It should toggle. So assume that the Q is initially 0. If Q is initially 0, As soon as the clock comes, it will check for T. If T is 1, it will simply toggle. Till what point? Now here, negative edge is appearing. T is 0, it will continue to retain the same value. After that, next clock edge, T is 1, it will toggle. After that, next edge, T is 0, it will retain the value, and so on. This is what we expect the output. Okay. Give this simulation waveform. T, this is clock. Again, I am saying be ready for both the examinations. In the exam, you may not have the simulators with you, so you have to be very specific with the syntax. If I don't see semicolon, I will deduct the mark. If I am seeing some space between end and module, I will deduct the mark, and so on. So the only thing which will make you proficient is practice. Yeah. So let me go back to the coding. And this, I'll simply modify the code itself. Okay. So instead of this, I will have T. Instead of D, I will have T. D flip flop नहीं, यहाँ पे T flip flop है. T. Better you should write your own code differently. Okay. Otherwise, the same will be replaced. T T. T here. Oh, not here. T here. That's it. Yeah. The logic should be when negative edge, no? Negative edge of the clock appears. Now, well, you'll have to check for one more condition there. Yeah. For that, yes, you have to specify if now in parenthesis you can write the condition. What is the condition? When T has to be happened, you can specify T equal to 1 like we do in the C, or you may simply write it as T. That's it. Then Q equals to Q bar well, just because this is happening sequentially, this is what we should do. But if it is not happening sequentially, if I am writing this kind of assignment, then you have to be careful. First, let me try this out. Clock is fine. Let's check for error. DFF defined. Oh, there. showing right result. And this one. Oh, negative edge of the clock is 0. Okay, specify the waveform properly. So let's say this is one. Initially t is 1, then I am making it as this 2 to 4. Alright, I think it's working fine for me. Should work for you as well. Getting output as expected. Now try making this change. Okay, what if you do like this? Everything will be executed at once, and then it will pop. It will give some different waveforms. Is this correct? And t is 1. Simply complement. Well, it is not giving, right? Correct waveform. So better way you should avoid this. Now you're good. Alright, everyone is getting T flip flop. किन लोगों को नहीं आया T? Try it out. We can specify the time scale on the top of this. There's some syntax there. I have to search for that. So I think there's some syntax for specifying the time scale also. Okay, the syntax is like this. Okay, the open quote, single quote. Okay, reverse quote you can say. I mean, opening quote, left quote, time scale, and then you need to specify the time unit and slash the precision. Okay, there is some syntax here. I'll have to check the syntax. In that sense, you can change. I mean, it's not required, but anyway, we can change it. So here we can specify the integers, integer precision only. So therein we can specify in points if you change this, okay, if you change the precision. Try it. First get the output for t, then try it for this. Okay, those who are done for T, go for JK. JK is not that easy. For JK you have 4 different case. So you'll have to use case. So again the syntax is more or less same like a for a C. Huh? Which one? एंड अच्छा इसमें इफ में अगर आपने एंड स्टेटमेंट से कंबाइन किया तो ना स्टिल इट्स वैलिड. आई मीन इट्स अ बिहेवियरल मोड. ओ एंड अगर यूज किया आपने तो ना इन दैट केस ऑल्सो इट्स अ बिहेवियरल मॉडलिंग जस्ट बिकॉज यू आर नॉट यूजिंग असाइन स्टेट. If there would have been assigned statement, then it would have been data flow modeling. And अगर आप keyword use करते हो, then it is a structural. I mean, it's in that case it's like a. Then why you need? I mean, it's kind of mixed modeling. Behavioral modeling you use when you don't know what is there inside it. You can very well use it. That will be called as a mixed modeling. Yeah, so this way you can specify the time scale. As I said, the time scale syntax is like this. You'll have to specify this. Okay, let me first run this. Yeah, this one. This is required. That, you know, kind of single quote, opening quote, time scale. This is, what is this? This is the unit, 1 nanosecond, and inside that how much precision you want. So it is 1 picosecond is the I have given as a precision, so that you can vary. मतलब 1 सेंटीमीटर अगर दिया है तो कम से कम आप क्या गिन सकते हो, 1 मिलीमीटर, तो समथिंग लाइक दैट. Now you can very well specify in point. Now that should be valid. So it's like 7.5 should be valid, 8.5 again should be valid, and so on. Yeah, I can specify that. Okay, so this you should remember. Okay, the syntax for time scale. Alright, go for JK flip-flop. Go for JK flip-flop. Again, I am saying that, you know, you should start slowly in JK flip-flop. First draw the block diagram. What actually you want. Is it running fine for you now? No? Even after closing it's not running. You can refresh the page. In fact, this Verilog or electronic design automation, there is a separate course for this, but we are learning in digital electronics, that too in first year. JK, Q, Q bar, QB I will write. Let's say it is a positive is triggered. And we know its behavior. I mean, when JK is 0, 0, it will retain the same value. When it is 0, 1, it will give 0. When it is 1, 0, and so on. Okay, we first, then, you know, you should specify the table. So this table indicates J, K, Q, and QB. It is 0, 0, it will retain as Q and QB, or Q bar you can say. 0, 1, 0, and this will be 1, 1, 0, 1, and this will be 0, 1, 1. Complement of this, and this will be iska complement. Okay. So we want to model this. So we have to have 4 different cases. So again I will modify the same thing. So go to the code. In this we need to specify the case, right? So whenever the clock edge appears, we want it to be positive edge, change it to pos edge. And now there are 2 conditions. See, we may go for if statement also, no problem, but as a just because there are 4 different, I am just avoiding 4 different if statements. So instead of that I can simply specify the case state. So the syntax is something like this: case in parentheses okay, what do you need to check? First there are two inputs, right? J and K. So let me specify them: JK, JK. Now we need to check for both J and K whether they are 0 0 0 1 1 0 1 1. So that you can do using this concatenation operation. So the braces indicate the concatenation operation. That means at a time I will check both J and K. And you should close it with in case. Now this is not required. Now the syntax is check if J and K is 0 0. So if you specify 0 0 0 1 1 0 1 1, by default the Verilog consider it as decimal. So you need to specify the base or the radix of the number you are specifying. So 0 0 are the individual bits, binary bits, 2 bits. So specify it's a 2-digit binary followed by what is the value of that. So what is this? This indicates the length of the number. This indicates the differentiation. I mean, it simply separates. So this is a digit, you can say 2-digit binary number which is 0 0. What if I need to write 3-digit decimal? So in that sense you need to write D. What if I need to write in hex? I may say it as a 1-digit hex as H, and I may say it as a A, and so on. So this is 1010. So this is equivalent to 4-digit binary as 1010, and this is also equivalent to two-digit decimal. Okay. All three of them are the same, isn't it? So I'll specify simply as I need to check 2-digit binary as 0 0. See, I didn't specify this syntax earlier just because I wanted to introduce as and when it is required. So there are lot of syntaxes. I mean, there are for loops, there are other loops also which are available. I'll introduce them as and when it is required. Okay, मतलब हमको जब जरूरत पड़ेगी उसको इंट्रोड्यूस किया जाएगा. Okay, new and new syntaxes. So right now we want to use this. So it's a 2-bit 0 0, and the output we want Q, right? So Q to be set as, you tell me, it will remain Q. And the other cases, I'll simply copy this 0 0 0 1 1 0 1 1. What is the case here? Q. उसके बाद यहाँ पे Q क्या रहेगा बोलो? 0 1 here, bar of Q, in case. That's it. At the input you need to specify J and K. Now this is a JK flip-flop. I will specify JK there, JK, here also JK. Again, now here I need to vary J and K. So initial J, let it be 0 0. See, again I may specify the inputs in vectors. You may do mixed kind of design. Okay, everything is valid, but you have to be syntactically correct. If there is a small mistake also, it will pop an error and it will deduct the marks. So you should be very careful. Again, I am saying it's now you may think that better to specify a long code but correct. But in the paper, I will specify that okay, you are restricted to only 10 lines of code, and then you have to be careful. So I'll specify JK00, 01. And this is the part of a lab examination also. Yeah, in the lab, whose lab is there today? Okay, for you, counters are done. In hardware, counters done, na? Now in the lab, you'll have to implement Verilog implementation. You have to go for Verilog design of all the designs which you have seen so far. I mean, आपने मल्टी सिम में आपने किया होगा, उसके बाद हार्डवेयर में भी किया होगा, उसका आपको स्ट्रक्चर सब पता है और बिहेवियर पता है. Then you need to code everything is in Verilog. That is what your lab will be. So those who have missed the initial portion of the Verilog, they may join in EC. Okay, I am going to begin Verilog there. Today 4 to 6. Alright, I think this should work. There may be some errors. Let me run this. There are some errors, I guess. Yeah, modules are missing. Okay, T-flip. Where is that? So here, JK. I'm modifying the same code. So, alright. Unable to elaborate this expression. Design 8. Okay. It should be comma here. That's it. The output coming. Okay. Let me make Q as 1 initially. Q as 0. So we have specified only the q value. QB has not been specified. So what you can do is you can always assign that. Assign QB as Q का complement, and then everything should work fine. Oh, times 2. Yeah, I think it's working fine for me. You have to be careful while giving this assign statement. Okay, in the assign statement here, if you specify QB as reg, then it will be a problem. If I simply specify QB so this assign, okay, the continuous assignment, okay, this assignment is not valid for register type. So but you can very well specify alright, I think this should run finally. Port Q QB output reading JK output. केस नहीं समझा, सिंटैक्स नहीं समझा, ओके, it's my mistake, sorry, I didn't explain it nicely. See here, what I'm saying is you can always use the case statement to check. We can go for if. Case statement is something like if a variable varies with multiple possibilities, then you can go for this case statement. The syntax is case in parenthesis what case you need to consider. So you want this JK to be varied, right? I mean if JK is 0 0, that is one case, 0 1, that is another case, and so on. If I simply specify J, okay, I mean we need to check both at a time. So what I've done is I can simply concatenate J and K using this concatenation operation, or called as a braces. So I'll just make it much wider. So I can specify J, comma K. Now what does brace indicate? It has concatenated J and K. Now this indicates at a time 0 0. So both we can check. Or else you can go for individual check also. Okay, this is not the only way to check. Followed by what are the cases? I mean JK, you need to check for J and K. What are the possibilities? Okay, JK may be 0 0, 0 1, 1 0, or 1 1, and followed by that you need to specify, with respect to this colon, you need to specify the output. For this you want Q to be Q, For this you want q to be 0, q to be 1 and q to be q bar. But if you simply write this, it won't work. It won't work, just because this is by default is taken as a decimal, so it will pop an error. So you need to specify this is like a 2-bit binary. So that we can very well do in Verilog using this syntax. What is the syntax? The syntax is, the first thing you need to specify what is the length of the bit you need to specify. There is a 2-bit, right? So length is 2, okay. 2 digit. What is the radix of that? Binary, okay. B. What are the numbers? 0, 0. That's it. So it's again a 2-bit binary. Digits are 0, 1. 2-bit binary 1, 0. 2-bit binary 1, 1. You can specify in decimal also, no problem. I mean, if you in decimal you'll have to specify in that sense. I mean, it is 0, 1, 10 and 11, that is. Is that okay now? And yes, of course you need to end it with end case. So this is important. How many of you didn't get this output? JK वाला output किन लोगों को नहीं मिला है? सबको मिल गया? Very good. So let's stop here for today.